does it have to do with nanoantennas? And then when nanoantennas are inserted in matter, then shot with laser, and then I tell you about how the dynamics is. So yeah, the NAPLIFE project is good. Okay, the NAPLIFE project is actually an experimental fusion research project, and it is just for proof of concept, and it is put together with various groups, also experimental and theory group. I'm in the theory group, but there is a nanotechnological group who fabricates the targets to shoot. There is a laser group who shoots the target, and then afterwards the craters and such things are then evaluated after shooting. So the main basic idea everyone wants to achieve in thermonuclear fusion is how to gain usable energy with more than we lose. So the loss has to be less than the gain energy, and hence we have to reach a higher gain factor. And from the definition, the thermal definition, it turns out that achieve with the Lasson criterion, we need to have high compression or big amount of time for the plasma, and this is actually the thermal criterion. So keep that in mind for later. This thermal criterion will give two kinds of approach. Try either to increase the compression or increase the confinement time. This separates into inertial confinement and then or magnetic confinement. And the latest these are experiments are the bestsellers. The newcomers are based in Germany. They have this is a stellarator. They tried and reinvented, but with another approach, the stellarator. It's a very promising one. And some boron proton fusion and this first light fusion, for example, is similar to what us will do. Like this actually shoots targets into each other, which is not just laser light. The targets are also shot. So it's kind of the little boy version of the fusion research. Also, since I last spoke, some experiments were done at NIF, the National Ignition Facility. They shoot actually from different from 192 lasers to the pellets, and they had a very good gain. But that is measured in kinetic energy. That's the trick. And the laser fusion actually separates into direct and indirect drive. We are on the direct part so far. The most successful so far was definitely with the highest budget, the National Ignition Facility, which is a drive. They have been doing it for longer, actually, the longest also. And the laboratory, unfortunately, is built in a way that they cannot change. As you can see from year to year, the approach is the same, only the material, they can only change the material, the lasers are fixed, everything is fixed, chamber is fixed. So they can only play with the and the whole RAM, which previously was gold, now uranium, and it works. So the playing with the target, we'll see later, it actually can work. And the main reason so far they have been hindered, that the National Ionization Facility, is the mechanical instabilities which develop at this even at 192 laser beams. They are not fully symmetric. There are imperfections, and this will yield when different density fluids are getting compressed. And the motivation for the NAPLIFE project, a concept that you don't really have to consider only the thermal criterion. And actually, this idea was learned from the relativistic heavy ion collisions, where in the shock frame, the boundary of the two fluids is mixed and fixed, and the material goes through, and that this also has means that the shock front can move at a higher speed than the speed of sound, or in this case the speed of light, because if we solve the relativistic Rankine-Hugel equations, which was written by Papp first and then corrected by Czernay, this proved to have another solution when the time-like discontinuity, we solve it from the time-like discontinuity frame, and then at points it's possible to have instant phase change, for example, because the phase change is dependent only on the initial condition and not the neighboring. Hence, this can be called the time-like detonation. And at constant absorptivity in the target, only 12% can burn simultaneously at such phase change. This is not actually also happening in the National Ionization Facility. And we found out that if we vary the absorptivity, then the simultaneous volume emission can be higher, nearly 7. And hence, we went with a simpler approach, mainly because it's more achievable here in Hungary too. We don't have 192 laser beams synchronized, and we consider only flat in quotations target, where we shoot from both sides, and the absorptivity target has to be in such a tricky way that it absorbs. Oops, sorry, I wanted a pointer. That it absorbs the energy of the light before it goes out on the other side. So And such the target configuration with two side shots have been also tried by, for example, by Bonesare and the University of China and colleagues, and they prove that they can reach a higher compression at a lower temperature. And here come the nanorods in help. This can be used to actually vary the absorption of the target as we go through. These are metal antennas which can resonate. And here modeling these nanoparticles usually is done by field simulations, which are using the relative permittivity, and also this is the half a grid simulation with a time domain simulation, just as particle simulations. However, the difference is that in particle simulations we can follow the marker particles, which are more representative than just relative permittivity cloud, because here, just as in real life nanoantennas, there are electron spill-out effects, which can hinder the absorptivity and the reaction of the nanoantenna later, as we will see it for later. This particle cell method was also invented at the Los Alamos facility, so very, very old, but it's still valid. As you can see, even in 2015, we used the epoch developed by Arber and all. The most powerful thing in the particle cell method actually is the particle shape that is covering more than one cell. So if you want to update the fields, you need to take into consideration which part of the grid interacts with the particle, and the is in half time. This is we update the fields at half time, then we call the particle pusher and then update the field for the full time. So, and we solve the relativistic equation of motion and with the Lorentz force on the master particle, and we use the deposition scheme where the charge density has to be constant. So as nanoparticles are metals, they also have resonances, and then resonance wavelength to a certain wavelength of light. And these are interesting part is that even though the nanoparticles are smaller than the half wavelength, there is an effective resonant wavelength. For the gold, we use gold. In the vacuum is around 133 nanometers. But here in the experiments, we use a so-called UDMA tagged copolymer, which is used, for example, for teeth hole filling of the teeth. We use that because the gold the solution which the gold nanoparticle comes in can be can dry harder, and the result will be a harder composite. So in an ideal world, we would have a nano antenna and shot from both sides. Remember, I showed you previously, this is actually a picture made here in the Wigner with transmission microscopy, that whatever we do, the orientation of the nanorods will be random. And also we checked what happens in the UDMA tegma if we are out of resonance. So we checked different wavelengths. Oops, sorry, I nearly spoiled there. This is a particle simulation, and the second picture is a traditional simulation. Here you show that you will see that our model is an agreement that we must be in the resonant wavelength in order to have the highest absorptivity or field enhancement. So sorry, I have to jump back. I forgot to mention that here in this marker particle model, we use for species, we defined 3 different species because in vacuum we only defined 2 species: the conducting electrons, which can freely move, and the gold ions, and we calculated with 3 conducting electrons, so that when we put together the number density of the 2, we will get a neutrally charged nanoantenna. And we did not model the complete UDMA tegma. For in this case, we modeled only the refractive index, but for further experimentation with the model, we used ionizable hydrogen. Dense ionizable hydrogen, first because it's an approximation and simpler, and then second, even with this, we have 5 type of species: the gold conducting electrons, the gold ions, which are there to keep the electrons there. Because of their mass, they will not move we tested at any laser pulse. And the other 3 are the hydrogen, which are not ionized, the hydrogen atom. Then later the proton and the electron of this atom, which after ionization they will be split, and the atom will be removed to the last species. So all the time the charge conservation is taken into account. And to come back to the problem here that we have to be in resonance, we checked what happens if we do a little difference from the orientation. Here in this the beam is traveling color to everything, to the polarization and the beamline too. So this is the, we call it the sleeping policeman. And remember this shape, the cross shape. It will be interesting. So this is the first problem when the first when it is in the polarization direction, and this next one is the cross quadrupole, which here shows that the field enhancement is very close to that one. And here you can see this blue indicates the where the original would have been, which was in the polarization there. And see the on the number density, the derived number density is staying quite there, so it's not moving too well. And 1 order of magnitude, this is the sleeping policeman, that is, and it's 1 order of magnitude less enhancement. And this is the light comes from here. This is oriented along the direction, and we would ask what would happen if the shapes are much more simpler spheres. Then the kinetic energy as function of time. The orange line is the original dipole in the polarization direction. We can see that even if the sphere is higher, the diameter is much higher than the 85 nanometer as the original. It set very lower regime. This is actually, it's not too big because it is at the 10 to the power of 15 intensity watt per square centimeter, of course. And here we use similarly the 10 to the power 15, which is very small. We have to consider bigger intensities, but 120 femtosecond. And the best polarized here is the magenta one, which is in the polarization direction. But here, check out the cross. We tried the cross because at least it can have it can stay in the polarization direction at least 2 times. I mean, in 2 ways. And for our surprise, at higher intensities, the cross can beat the polarized one, simply because there are more conducting electrons. And so to conclude, these cross quadruples are very advantageous, and they are irrespective for the orientation. We tried in different angles too. We nearly achieved the same high protons. And the proton emissions from the neighborhood of the nanorod shows that they follow the protons which are closer to the nanorod, and the majority of the protons will follow the nanoplasmonic events generated by the conducting electrons. And also, this has been generated by the Debrecen group, by Maria Chete, with a Coca-Cola bottle-shaped nanorod, and they achieved high intensities, and we consider this mainly to direct the protons in one direction. We try to build up a direction for the protons, and we can control the directions too. Then we have more control. And thank you for your attention, and thank you for the GPU lab to use the resources.
Speaker, maybe for a few short questions, if there is any.
I forgot to, if someone asks to watch a video, then I can show.
The PIC simulation code, was that your development, or you used some package?
No, I used a package they developed for 15 years. It was a Fortran. This epoch, I'm sorry, I probably did not mention in detail. It was written in Fortran, and they still developed it. Mm-hmm. So they still used it in 2015.
Okay, thank you.
It is a very detailed code. They also have Bremsstrahlung, and they have quantum electrodynamics too. So it's the work of 10-20 people in the range of 15 years.
So I'm a little confused about these shapes. So the rod, so the cross is better than the rod, isn't it?
Yes.
Yes, but the sphere is worse than
the sphere. All of the spheres were worse.
Is the worse. But also the Coca-Cola shape is also better than
the Coca-Cola shape. We did not test in the PIC. That is the tradition tested by the traditional method. So they know what type and what shape resonate, and we then implement that in the PIC code. Mm-hmm. We calculate the number of conducting electrons in that type of shape, and then try to implement it.
Okay, the question, but if we had a flat cylinder, so something which is further, so like the further going, so if cross is better than the rod, I would suspect that the flat cylinder is even better, because it has any direction where it resonates. But I'm not sure.
Flat cylinder.
Yeah. So it's
one side.
Coin.
Oh, a disc. Okay, disc. Yeah, disc we have not tried yet, but it's a good idea. Thank you. I will implement it later today.
So I got signals that we should wrap it up. So thank you for your attention, and I'm giving the final words.
Yeah, the father. Okay. Oh. Thank you very much, and thank you.
Right, the video. So the yellow are the electrons, the orange is the gold ions, and this is at very high intensity, and the electrons are blown away after 40 femtoseconds, just as in reality. Okay.
Okay, the mic is you. Okay, so we are at the end of the 14th GPU day. What is coming is the 15th one next year, approximately the same time. Don't forget that we are planning to have the lectures on modern computing in science, and we just already started to thinking on what could be the topic for that, and these are the the large language models, which we are planning to do some application from scratch as usual. So a few words about this event. So we had about 30 talks, which was, I think it was very dense and very many interesting things, both from the technological part of GPUs and the physics of what you can do on GPUs. I really appreciate all of you who presented and joined us with us. We will put up the talks soon after the conference or GPU days, and also the videos will be uploaded to the GPU Day YouTube channel, so you can go back and see the things. And I really appreciate that you could stay here until the very end. And I would like to thank you for our supporters, which was the Raster Grid Limited, the KIFU, the Wigner and the Hungarian Research Networks, and of course the Lombic, who support helped us to organize this and to have a free lunch, of course. And of course, I would like to really thank my colleagues, Gábor Bíró, Balázs Kacskovics, Balázs Szigeti, and Dudás Bence, who helped us during the organization, and of course the nice hosting by the Wigner Data Center. Yeah, Adam is over there. So thank you very much. See you next time, a year from now. And now the party is over.